Hello everyone, I am Shou Kang from Imperial College London. It's my pleasure to present our latest work, WiMANS, a benchmark dataset for Wi-Fi-based multi-user activity sensing. WiMANS is the first dataset for multi-user activity sensing based on Wi-Fi. It contains 9.4 hours of dual-band Wi-Fi channel state information, CSI, along with synchronized videos, recording the simultaneous activities of 0 to 5 users. WiMANS also provides the first benchmarks for Wi-Fi-based multi-user activity sensing. Human sensing with Wi-Fi CSI is an increasingly promising alternative to traditional sensing technologies, thanks to its non-intrusiveness, environmental robustness, and device-free merits. In Wi-Fi-based human sensing, much effort has been devoted to three underlying yet distinct tasks: human identification, human localization, and human activity recognition. However, several critical drawbacks seriously hamper the practicability of Wi-Fi-based human sensing. Firstly, it's the single-user limitation. Existing public datasets only include a single user in each CSI sample. Although recent studies have attempted to sense multiple users simultaneously, there remains a lack of public datasets that enable Wi-Fi-based multi-user sensing. Another challenge is the insufficient modalities and annotations. Most datasets collect CSI of a single Wi-Fi band and do not incorporate synchronized videos, restricting the use of Wi-Fi CSI in various sensing tasks. Finally, no benchmark is available for multi-user activity sensing based on Wi-Fi CSI. To help resolve the above drawbacks, we present WiMANS, the first dataset that involves multiple users performing different or identical activities simultaneously in each sample, as shown in this table. In WiMANS, each sample includes 0 to 5 users performing identical or different activities simultaneously. We collect 11,286 CSI samples of dual Wi-Fi bands, 2.4 and 5 GHz, as well as synchronized videos. All samples are annotated with user identities, locations, and activities. This is also the first benchmark for the multi-user sensing performance of Wi-Fi-based models. Here are some examples of Wi-Fi CSI in videos involving different numbers of users, different environments, and different Wi-Fi bands. Each CSI sample lasts for 3 seconds under a rate of 1,000 As, using a transmitter with 3 antennas and a receiver with 3 antennas. Each pair of antennas is equipped with 30 subcarriers. Therefore, the dimension of each CSI sample is 3,000 times 3 times 3 times 30. Each video sample lasts for 3 seconds under a frame rate of 30 Hz, with 3 RGB channels, and the frame resolution is 1920 x 1080. Therefore, the dimension of each video sample is 90 times 3 times 1920 x 1080. We include 9 daily activities and 3 daily environments in our dataset. The layouts of environments are shown in these figures. Specifically, we designed simultaneous scripts to instruct users to perform identical or different activities at varying locations independently yet simultaneously. We annotate our dataset by groups, where each group corresponds to a specific number of users and environment. Finally, each label corresponds to the environment, Wi-Fi band, number of users, identities, locations, and activities. Here are the statistics of WiMANS. In each distribution, all categories have almost equivalent proportions to construct WiMANS as a relatively balanced dataset. We utilize WiMANS to benchmark the multi-user sensing performance of 8 state-of-the-art Wi-Fi-based models and 6 video-based models, as listed in this page. Here is the performance of Wi-Fi-based models for multi-user identification, localization, and activity recognition. Generally, we can observe that Wi-Fi-based models show desirable performance for multi-user identification and localization, while there is still vast room for improvement in multi-user activity recognition. We analyzed the impacts of user numbers on the performance of Model THAT. As expected, sensing more users simultaneously results in lower recognition accuracy. We provide the performance of video-based models for comparison. Overall, video-based models achieve better performance than Wi-Fi-based models. Such results are expected since video-based analysis has been well studied in computer vision, which also demonstrate the quality of WiMANS, where users have performed distinguishing activities. Finally, we compare Wi-Fi-based models with video-based models in terms of model complexity and time efficiency. These results signify that Wi-Fi-based human sensing can achieve satisfactory performance with better cost-effectiveness than video-based solutions. We acknowledge that there are several limitations of our dataset because we only include daily activities and do not consider challenging conditions such as obstacles. Meanwhile, we do not discuss the use of various Wi-Fi devices in our work. In the future, we will further investigate multi-user pose estimation, dual-band augmented sensing, and cross-domain sensing. Thank you very much for your interest in our work, WiMANS, the first dataset for Wi-Fi-based multi-user activity sensing. Please feel free to contact us if you have any questions about WiMANS.